Hey everyone, today we are looking at modeling polynomial functions. So actually using some real world examples to apply polynomial functions to. That's what's meant by modeling. Working straight out of textbooks today, we are on page M2-103, and this is the last thing we're learning about with polynomials. So good news, this unit is almost done. We got a couple things here, like lays out the learning goals on this page. To model a situation, they're probably not going to follow a polynomial function exactly, and that's what's meant by regression. We can model it using a function pretty accurately sometimes, and when you model it, you can then predict what's going to happen at any given point, and we're also going to sketch some functions that can model the situation just by hand. Here's some key terms that we need to know. So the regression equation is what models the real-world data. The coefficient of determination tells you how well it models that data. So we'll get into these key terms later on. For now, we'll just get through one of these warm-up problems. We are going to need to use technology to determine the linear regression equation. So this is using, obviously, linear data, stuff that can just follow a straight line, rather than polynomial where there's a bunch of curves. So I'll recap with you how to do that. You are going to need a graphing calculator to do this. Now, the first step in getting the regression equation, and again, it said linear, so that's why I'm using this, mx plus b. I'm going to hit the stat button, and then I will hit enter. Now I've got all these lists here. In list number 1, I'm going to type in the x values here. So I'm going to type in 3, hit enter, type in 7, and then -2. I'll scroll over to the next list, and this is where the y values are going to go. So you can see how I have the points, right? 3, 4, so I need to put a 4 here. The next point is 7, 6, I'll put a 6. And my next point is -2, -4. Okay, so let's see what this graph looks like real quick. We've got the data plotted. Now if I hit graph, it should show me those dots. Here's my point at -2, -4. Here's my point at, that one would be 3, 4, and this one is 7, 6. So we're looking for the equation of the line that's going to go like that. What models this data pretty well? Like what equation, when I plug -4, or when I plug in -2 into that equation, it spits out something pretty close to -4. And the same thing for when I put 3 into that equation, it's going to spit out 4. So your calculator is going to do all of this stuff for you. All we'll need to do to get this equation is go to stat, go over to calculate, and again, we're doing linear regression. There's 2 different options. Because it's algebra, we'll just go with this one. That is mx plus b. The a, the m, both refer to the slope. So anyways, I hit enter. It's going to ask me some questions. What are the x values? Well, I type those into list number 1. My y values I put into list number 2. You don't have to worry about this at all. It's how many times you want to pull the data. You can store this regression equation into your calculator, but let's not worry about that. So just go to calculate, and it pulls up all of these values. So the ones that we're concerned with are the a and the b for now. That's how you get the regression equation. So anyways, the regression equation for this is y equals. So again, this a value is where I'm going to get my slope. Looks like that would be 1.13. My x is gonna change. My x is what variable or what value I want to plug into it. And then the b value that I got from the calculator was -1. We'll just round to like there's 100, so -1.02. And that's it. That is the regression equation for this set of data. You can practice this if you want on your own and do number 2 and number 3. Now, I just want to show you one more thing. If I go to y equals, this is where I can type in equations. So if I type this in, 1.13, well, let me scroll over to where I can actually type 1.13 minus, well, I need to put an X there as well. Goodness, the X button right here, right underneath mode, minus 1.02. Now when I go to graph, it'll put the line up there. And so that is the best line possible that will model these 3 points of data. That's exactly what we're going to do with polynomial functions. Okay, so let's turn the page and answer some of these. So it gives a pretty decent rundown of what regression is. Again, it just models a relationship between two variables in a scatter plot. Exactly what we did here. There's our scatter plot. We've got the points plotted. The line models those points. Gets you close to all the possible points. Can be used to make predictions about future events. Any degree polynomial can be modeled by a scatter plot, but data generally has one curve that best fits the data. You may also recall the coefficient of termination. R squared is the variable for it. Measures the strength of the relationship between the actual data, the dots that I plotted here, is the actual data, and the regression equation, which again is the line. The value ranges from 0 to 1. 1 is a perfect fit. So if I go back to my calculations for that regression equation, you see I have an R squared value of 0.929. That indicates we've got a pretty good coefficient of termination. We have a very strong relationship there between the data and the line that we created. So this is going to be a very important value as we progress through this topic. Okay, so sketch the given polynomial, then draw 10 data points on each coordinate plane where the coefficient of termination is going to be close to, but not equal to 1. And then you can use technology to determine the regression equation and R squared for the data. All right, so this is going to take just a little bit of time. So a polynomial of degree 2, well, we know what that is. That's quadratic. Quadratic. So the quadratic function is a parabola. Maybe it looks like this. Okay, and then we want to make this a very strong relationship, coefficient of termination close to but unequal to 1. So what you would do is, I guess for this problem, is just kind of put some points near the line, but not exactly on the line. We wanted it to be close to 1, but not exactly 1. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's do 10 up here. Okay, so I'll walk through this one. Again, so you input the actual data. We would need to go to stat and then hit enter. There's list number 1 for the x values and list number 2 for the y values. So let me clear these. All right, so this first data point, it is at 1, 2, 3, 4, -4, -4, and 8. Next point, -2, 7. This one is at -2, 1, 2, 3, 4. All right, so we got 3 of our 10 points. This next one looks like that's at 0, 4. Next point is at 1, 1. My next point is at 3, 3. All right, next one is at 5, 2. And then I go to 6, 5. Oops, that's not where the 6 goes. 6, 5. Oh, 6, 5. So this one must be 7, 7. I think. If we haven't made any mistakes so far. So my next one would be at 8, 9. Okay, so let's graph this and just see what it looks like. I need to take out my original line actually. Just go like that. So that's not going to model this data. All right, so that looks pretty close to what I created on this graph. See, we got this series of points that goes down and then shoots back up. Again, so this should be modeled by a quadratic. Looks like the A value might be kind of small because it's pretty smushed vertically. So to do this one anyways, the quadratic regression equation, it works very similar to the linear one. We can just do this all in the calculator. I can hit stat, scroll over to calculate, and of course, instead of doing linear regression, I'm going to be doing quadratic regression. It's going to ask you the same exact questions. We can pretty well skip most of these and just go to calculate. So here's your general form for a quadratic equation. So let's jot that down real quick. Just for reference, we know that y is equal to ax squared plus bx plus c. And this calculator gives us those values. We know that a is equal to 0.184. X squared, and then the b value is negative 0.75 with the variable, and we've got the c value, the constant, where we're crossing the y-axis, is at 2.81. Okay, so what I'm going to do now is just see how well that function, this equation, represents this model of data. So let me go back to y equals. I'll type it in here. We got 0.184x squared minus 0.75x plus 2.81. Okay, if I go to graph, it should build us a nice quadratic, and you can see it fits that data really, really well. That is the best quadratic equation to model this data. Now, one more thing, if I go back to calculate, and I go to quadratic regression, our r squared value is 0.81, approximately at least, which indicates that it's a pretty strong relationship. I didn't get it quite to what this was asking for. It wanted the coefficient determination to be close to but not equal to 1. I could have done that just by making these points closer to the actual line that I sketched here. Make it more, or make it easier to be represented by a quadratic equation. But anyways, that is the idea behind regression. Like for this one, polynomial of degree 3, if I sketched one, and every point I plotted on this graph, like here and here and here, my coefficient determination would be equal to exactly 1. Like this situation is modeled perfectly. To decrease the coefficient of determination, or that r squared value, to bring it down, the points just have to be not so perfectly aligned. Like this is now not exactly equal to 1. This would be equal to something a little bit less than 1. But again, that's going to wrap it up for this video. I did pages M2, 104. Thanks y'all for watching. Hope you have a better idea of what's meant by regression. See you in class. Bye-bye.